SwayamPrabha. Digital India. Educated India.
Let us start this lecture with a thought process. Power does not corrupt a person, it only reveals the corrupted mind of a person. That I have observed during my lifetime, that people are having wrong notion that power corrupts a person, absolute power corrupts a person absolutely, which was stated long time by Louis IV, and but that happens to be not the right. So, let us recall that what we learned in the last lecture. In the last lecture we discussed about the Saint and Robert law little more detail by considering the practical range of the propellants, and we have observed that the pressure index varies from around some 0.2 to 0.6 in the case of most of the propellants. And later on we also looked at how to enhance or the reduce the burning rate. There are two ways of doing that. One is by changing the composition of the propellant and also the method of processing a propellant grain. Other is by changing the operating parameters in the rocket motor itself. We have seen several ways of doing that, and some of them already we have discussed, like chamber pressure, propellant temperature and flame temperature, and of course certain things we have not discussed. Maybe today lecture will be covering them, that is your erosive burning and the acceleration of the rocket motors, and additives, the particle size, and then oxidizer content in the propellants. One can also change the burning rate. So, let us now discuss about the effect of acceleration and particle size on the burning rate. And as I told earlier, that the rocket motor can be spun around, particularly in the missiles, and sometimes to have a stability it should be also spinning around it, and it may be subjected to acceleration. As a result, that this fluid inside the combustion chamber will be rotating, and it will be giving like acceleration to perpendicular 90° to the flow of the gases, in particularly in side burning grain. For example, if I say this this is your side burning grain, right, which is having this is your grain. Now, if it is rotating, if I say this is my axis and it is spinning with a omega rotating, then what will happen? This fluid will be inside this gas, this is your port. The gas will be perpendicular to this, and the flow which will be taking place along with these directions, right, and this acceleration which will be occurring, the flow is occurring in this direction, and the acceleration will be in this direction, because the fluid is rotating, it is moving around. So, therefore, there will be and it will be making 90°, and this effect will be predominant from 60° to 90°, and there is an increase in the propellant burning rate. That is being data being plotted here, the burning rate augmentation, that is R A due to acceleration divided by the R dot without any acceleration. So, this has been plotted with the acceleration g is being in this axis, it is from 0 to 150, and for 3 set of data, that is one PBAA, that is polybutadiene acrylic acid, 16% aluminum 26 micron size, the rest of the things will be basically the oxidizer, and BU is your double base propellant, and of course, the 3% is aluminum, and then E107 is polyurethane, 18% aluminum, and the particle size is 29. Of course, particle size is little bit changing, and this chamber pressure is 3 megapascal. As I told, this 90 degree, that means this is the propellant flow rate or the gas flow rate. The angle of the acceleration which will be there in this, and this degree is 90 degree, because of centrifugal force this is acting. So, keep in mind that when acceleration is 0, the burning rate augmentation ratio is 1, that means it is same as that without acceleration. As it increases, it is increases little bit, and then of course, it will be much higher with the increase in acceleration. But in case of the BU, that is double base propellants like combined one, that you will find it is increasing, but this there is a increase in the burning rate augmentation for a particular pressure, right. But for E10, so polyurethane, that increase is much higher for the same acceleration, that is 100%. Of course, acceleration is more, means the effect of this acceleration on the burning rate becoming very high, and that is the thing. That means, it is depending on the composition of the propellants. So, we have seen that there is a burning rate augmentation with acceleration, and also the burning rate gets affected by the composition of the propellant as well. And when you will do that, there will be also affecting the thrust, and let us look at without any spinning of the rocket motors, that is 0 RPM. Let us say that you will be getting a thrust which will be remaining constant, and it is the same amount of propellant will be burning for a let us say 3 seconds in this example, right. And as the RPM increases, let us say 673 RPM, you can see that in the beginning, maybe with the time there will not be any change, but as it started spinning, then there will be increase in the thrust level, because of fact that the effect also will be less. And let us say in this example, like it is subjected to 21 G, but as the propellant get consumed, and then the radius of this radius will be increasing, because the fact that this will be receding part, and this radius r will be increasing. If this r is increasing, then the acceleration effect also will be increasing for the same RPM. So, therefore, the thrust goes on increasing, of course, towards the end it will be reducing. You can notice one thing is that the more propellant is getting consumed due to the augmentation of the burning rate. As a result, there is an increase in thrust. However, the duration of burning of the same propellant is being reduced, and similar situation also occurs when it is rotating at let us say 910 RPM. There is a sharp increase of the thrust in this range, but also the acceleration is changing from 38.5 G to 52 G. So, this is the important aspect you should keep in mind. It is not that acceleration is remaining constant during the entire burning of the operation of the solid propellant. It is also changing because the radius of the port is changing, or rather port area is also increasing. Let us now look at the effect of particle size and also the propellant temperature. So, that is the data is basically burning rate versus the chamber pressure. You can see that let us say 243 Kelvin, that is basically the T p, that is propellant temperature. Let us look at the effect of particle size, and if you look at this is AP stands for ammonium percolate, and in this case propellant basically ammonium percolate is 40%, STPB is 20%, and metal powder loading, that is aluminum, is around 40%, and Fn is corresponding to basically 200 and 400 micron particle size, two generally being used, and you can note that this point corresponding to the 243 Kelvin and lower burning rate, and of course, the burning rate increasing with the chamber pressure in this log-log plot. And when the temperature is increased from 343 Kelvin, there is a increase in the burning rate having the similar nature of the curve. And you can also note another thing, that is your when the particle size decrease, that you can find, that is your at the lower temperature there is a increase in the burning rate, this corresponding to this one for at the lower temperature 243 Kelvin. So, for a particular chamber pressure, if I consider these two, the particle size, there is a order of magnitude difference at the same temperature of 243 Kelvin. If you look at this is around something maybe closer to 3 mm per second, whereas if I consider this as that, it will be something around 6-7 mm. There is a twofold almost increase in the burning rate, and when the temperature increases, of course, the burning rate increases for the same particle size. So, therefore, the particle size becomes smaller, then the flame will be closer to the burning surface, and therefore, the more heat will be transferred to the burning surface, such that the burning surface propellant will be regressed quicker, such that the burning rate will be increased. So, let us look at a little bit further about the effect of particle size on the regression rate in case of a double base propellant, and also where we are adding the ammonium percolate. So, if you look at this experimental data, this is burning rate is plotted in centimeter second in the vertical axis, in the horizontal axis is pressure. You can see one very interesting here, when the double base propellant without any ammonium and the particle size will not be there. So, this corresponding to this data, this is your double base propellant, and you can see that the plot in this case, of course, it is burning rate is increasing with the chamber pressure, but however, it is not linear in this log and log plot. It is a little curved, and that is defying the law what we had learned, that is Saint and Robert law, that is A P C power to the n. So, according to this law, that is this plot could have been linear, there is a slight increase in that. And when this is now the modified double base propellant, that is and when you add this 20% of AP, then you will find there is a increase in the burning rate for a particular pressure, and you can say that for a particular pressure, let us say it is something around maybe 14 atmosphere pressure, there is a slight increase in burning rate. And this also again is a curved one, and when you increase to the 30% ammonia with the same particle size of 150 micron meter, there is a also increase in the burning rate. However, the curves is little non-linear in this log-log plot also, it is not a straight line. However, when the particle size is reduced to 18 micron meter, you will find substantial increase in the burning rate as compared to this other case like AP 30%. So, therefore, what we can learn from here that sometimes the relationship between the burning rate and chamber pressure need not to follow this Saint and Robert law. This is Saint and Robert law or the Vallée law, right. That is the one thing. Other thing is that when you add the ammonium perchlorate to double base propellant, there will be increase in burning rate. And when you reduce the particle size of the ammonium perchlorate in this combined modified double base propellant, then you get basically enhancement in the burning rate. So, let us look at the erosive burning. As I mentioned earlier, erosive burning is basically can occur only when the velocity of the gas inside the port is much higher as such that it will be affecting the regression rate. For consider, let us say that this is your propellant grain, right. If you look at this portion is your side burning propellant grain. And when this will be regressing, suppose let us say this is regressing back, then what will happen? The material will be coming over here, and on the both the surface will be converted into gas, and it will be moving toward that the nozzle, and this is your nozzle. The flow will be coming toward that. And keep in mind that when this mass being added, this mass will be added, this will be mass of the gas. That means, this propellant will be converted into the is equal to the mass of the gas. I can assume sometimes there will be accumulation of that, and then this velocity of the gas, if I say this is Vg, this will be goes on increasing along with the length of the propellant, length of this port, and you can say this is your L. So, that means this velocity of the gas will be increasing towards the end of this propellant grain. So, and if it will go beyond certain limit, then what will happen, that there will be a lot of mixing between that, and then heat transfer from this hot gas. That means, there will be some heat transfer which will be taking place. The heat will be transferring to that, and that is your heat transfer from gas to propellant surface, and that will increase the regression rate of the propellant, and this will be occurring particularly for a longer side burning grain, and also in the initial stage where the port area will be smaller as compared to the throat area. This is your throat area, and if you look at this is my port area AP. So, then at that time the erosive burning will be occurring, and this can occur only when this Vg will be crossing certain threshold value. You can see this erosive burning right, and this erosive burning ratio is basically, if we consider R dot EB is nothing but your R dot, which is the normal burning, like we have seen that thing without any erosion of the propellant, plus R dot E. If I divide this by this equation by the r dot E, and this is r, sorry, if I divide this basically r dot, and this will be equal to 1. So, I will get is 1 plus r dot E divided by r dot. And keep in mind that this we call basically, this is known as the erosive burning ratio, right, and this is nothing but your r dot E b divided by r dot. So, you can see from here that erosive burning is remaining constant for a particular reference propellant grain, and it will be remaining almost constant. Then this is your threshold value. That means, when this velocity, this is your gas velocity, will be 100 meters, then there won't be any change in the erosive burning rate. That means, erosive burning ratio is equal to 1. And after that, when the velocity increases, this goes on increasing. Of course, if the lower energy propellant is there, then it will be occurring at a little earlier stage, and if it is higher energetic propellant as compared to the reference one, it will be occurring at a higher gas velocity. And if I look at this R b by r dot, and that will be, I can express as 1 plus C, right, there will be, and then into G power to the 0.8 and G dash, and this is your Hepside function or the step function, where the C is a constant and G is the specific mass flux rate of the main flow. And keep in mind that this r dot, we know this is A P c power to the n, and this is basically your Saint and Robert law, and where there is no erosive burning, this r dot will be prevailing. And this G is the specific gas flow, is nothing but rho G, that is the density of the gas, which will be dependent on the chamber pressure. V G is the gas flow velocity, and rho P is the density of propellant. R dot already I have explained, that is the burning rate of the propellant without any erosive burning. And R E P is basically Reynolds number of the port. This is your port area, this is your port area. Threshold specific mass flux rate, and which basically happens to be 35 kind of things by corresponding to certain data which was given by Mukunda and Paul. And as I told, H G by G star is Hepside function, that means it will be remaining 1 or 0. As I told, V G is the gas velocity over the propellant surface, and erosive burning can be minimized by designing with a large port to throat area. If this port area is larger as compared to the throat area, this is 80, the throat area. So, beside this, if the length of the propellant grain is smaller, one can also, erosive burning must be avoided, because it will be creating problem. Keep in mind that erosive burning will be occurring only in the initial stage. Later on, when the port area gets increased, this effect will be nullified or reduced. So, as a thumb rule, AP by AT is less than 4, then for L by D ratio, then erosive burning will be occurring, and if it is greater than 6, then naturally it will be not occurring at all. Similarly, when AP by 84 should be used for grain with the larger L by D ratios, such that one can really avoid the occurrence of erosive burning. So, you can see that there is a various ways of eliminating the occurrence of the erosive burnings, and we will see what is the implications of occurrence of erosive burning in a solid propellant rocket engine in the next lecture. With this we will stop over. Thank you very much.